Friends, here this is our first lecture. We are going to discuss history of electrical engineering. History of the electrical engineering introduction. While discussing about the history, how electrical innovations took place, it took years to find new concepts and electrical engineering fundamentals. So we classify these in three periods how these innovations took place. First one is the old age, second is middle age, and third latest renaissance, 16th and 17th century. We can see first this charge time. This means charge time means only charge was observed by this 16 in ancient world. Here first known account of charging of amber. This observation was done in Greek, ancient Greek, before Christ 600 years. And then secondly record comes after 1000 years, AD 1600. So there is a big gap that new finding come after the 1000 years. 1000 years there was no research. Why this occurred? Because in 5th century Rome Empire was ruined by Goth, Hun and Slovenian tribes. These tribes invaded there and spoiled the Rome Empire. And then it took about 1000 years. Europe had the dark time of Middle Age. So in AD 1600, the term amber was termed as a electric. Next, in 1661, mechanical means of inducing charge. So here induction of the charges was observed. In 1675, electrostatic repulsion and attraction were observed. In 1729, conduction of electric charge. In 1733, two types of electricity defined, like positive and negative, means attraction and repulsion. In 1745, Leyden jar. This is the device which allowed to charge storage. Here this capacitor or condenser, we can say, was invented. In 1746, circuits and currents were defined. In 1751, Benjamin Franklin published theory of electric fluids. In 1785, electrostatic repulsion, positive and negative charges were defined. In 1800, voltaic pile allows controlled discharge of charged particles. So here discharge was successful, superseding the electric fluid theory. So this voltaic pile is the first battery. Here we observed from AD 1600 to 1800. This in this period, the charge was observed. Some attractive forces, attraction and repulsion forces were observed. Force was observed. So earlier 18th century, these were the findings or innovations related to the charge. So this era is called charge times. related to charge. Innovations were related to charge. So this is charge time. The most significant discoveries were made in period 1819 and 1875. This is the flourished era, we can say, in Europe. Cultural and arts in Europe were flourished in 16th and 17th century. In 1819, the link between the currents and magnetic fields were observed. In 1820, currents and magnetic fields used to create motion. Here, motion was observed, and it laid foundation to the motor research. In 1825, electromagnet was developed, allowing stronger magnetic fields to be used. In 1826, Ampere law defines relationship between the magnetic flux and current. In 1827, Ohm's law introduces concept of impedance. This formula V is equal to IR or IZ. Admittance of the circuit also come in picture. In 1830, Henry explains self-inductance. Self-inductance, it is due to the flux linkage. Self-inductance of the n d phi by dt. In 1831, Faraday's law explains mutual inductance between the circuits. The transformer is good example for this. Lenz's law explains electromagnetic induction of motion. Here it is motor, we can discuss in later second lecture. In 1835, Gauss' laws describes magnetic and electric flux. Latter holds for gravitational flux. This was also research done in 1835. In 1840, Joule's law explains resistive heating by the current and contributes to the law of conservation of energy. Here, this heating was related to the I square R. In 1845, Kirchhoff's voltage and current laws aid circuit analysis. This is also Kirchhoff's voltage and current laws were invented or were innovated in 1845. In 1853, Helmholtz publishes circuit reduction theorem. So, to reduce the large circuits so that it is easy to solve the circuit networks. Later, the Norton and Thevenin's equivalent circuit theorems. Norton and Thevenin's. From source to load, there these networks became more complex. So complex networks were solved for power flow study. So network analysis was required. In 1873, electromagnetic theory condensed to Maxwell's equation, which predict the electromagnetic nature of light. So here one new understanding, light is in the form of electromagnetic waves. In 1883, Tesla's first attempt to sell the polyphase induction motor. Polyphase alternating current idea means polyphase, like this is, we can say single phase and three phase 4-wire. So polyphase was the having higher power capability. In 1887, Hertz confirms that light is an electromagnetic waveform. So this light is an electromagnetic waveform. This was the confirmation which lead to the communication wireless communication department. Means we put laid foundation of wireless communication. Due to this electromagnetic waveform form of the light. We will discuss some list of scientists and their observations. First is Thales of Miletus. His observation was before Christ 600 years. First known account of charging of amber. Here what he observed, or he has just written the observation done by the Greek people in ancient times. The ancient Greek observed as early as 600 years before Christ, then amber is rubbed vigorously against the cloth or wool. It becomes charged, attracting the other particular materials. This is drawn from the second-hand account of the writings of the mathematician and natural philosopher Thales of Miletus. Thales of Miletus has just recorded what the Greek people observed. Those observed that the amber is rubbed vigorously against the cloth or wool, it becomes charged and attracts the particular materials. Unfortunately, none of his works survived. The charging of amber had to wait around 2200 years before receiving its common name, electricity, the derivation of the Greek word amber, which was termed later as an electron. So electron was the word replaced by the amber. Amber was the word replaced by the electron. Secondly, William Gilbert in 1600, amber-like material dubbed electric. He just coined or termed the word electric. What was the observations done by him? Here he published his treatise on magnetism, De Magnete. For this work, he investigated other materials that could be charged in the same manner as amber. He just tried to understand if other materials than amber get charged or not. To describe this effect, he coined the term electric. So this William Gilbert is the founder of the word electric, meaning like amber. In the 150 years following Gilbert's investigation, although a series of important inventions and observations were made, little progress was made towards understanding the nature of the electricity. Then this William Gilbert in 1661, mechanical means of inducing charge was observed by the Guericke, Otto von Guericke. Two metallic balls, we can say. First one is positively charged and second is not charged, but due to this first metallic charge having positive charge, this will induce negative charge in the nearest metallic ball. These metallic balls, we can say metallic balls with opposite charges. First, this is positively charged, will induce negative charge in nearest metallic ball. Also, suppose this is a cloud with the positive charge. In rainy season we observe this, and if the lightning strike is there, and this will induce the negative charge on the earth's surface. This is also the phenomena we can understand, the inducing charge. In 150 years from the Gilbert's investigation, although a series of important inventions and observations were made, little progress was made towards understanding the nature of electricity. Here, these innovations and these findings were not instantly. Many centuries took place to understand new concepts, how charge is stored, how charge is generated, how means that time everything was blank. There was no electricity and no research, previous research. So these scientists were just observing the phenomena, what is happening. They were just experimenting and observing the results. Then in 1675, electrostatic repulsion and attraction was observed by the Robert Boyle, chemist Robert Boyle. What he observed? He observed that electric force would travel through the vacuum and the repulsion and attraction of the charged objects. So there is a repulsion and attraction of the charged object. In 1733, Charles Francois de Quistenay-Dufay stated that there were two types of electricity. We can say positive and negative. These two, attraction and repulsion forces, were observed at that time. At this stage, the understanding of electricity was still restricted to the charged objects. Only charged objects were observed. Charged objects were observed by repelling and attraction. Repelling and attraction, these two phenomena were only observed. In 1729, conduction of the electric charge was observed. Conduction means this charge was just stored, but now their further progress was conduction. This concept came in picture. Conduction. Here attraction and repulsion was the finding. First one, attraction and repulsion was the finding. Secondly, this conduction phenomena was observed. Who is the scientist? Is Stephen Gray. He observed the conduction. Stephen Gray observed conduction phenomena, conduction of the electric charge. Discovered electric charge could travel or to be conducted through the certain material. So certain material was a conductor. So this led to the conductor and insulators. These two phenomena were again observed. Some materials were conducting and some materials were non-conducting. So non-conducting were called insulators. Further, in 1733, two types of electricities were defined. Two types means we can say positive and negative. In 1733, Charles Francois de Dufay. So this Dufay, what he stated, there are two types of electricity. He just confirmed. He stated there were two types of electricity. There are practically there are no two types, but positive and negative. Attraction and repulsion force. He called attraction and repulsion force as two electricities. So further, in 1745, Leaden jar. This was the device which allowed to store the charge. Charge storage was observed in Leaden jar. That was the first device which was observed by Peter van Mozambique in 1745, the University of Leiden. So Mozambique was the first one to observe the battery or condenser. Developed device that would allow electrostatic charges to be stored and then discharged. So he observed charges to be stored and then discharged. This became known as a Leaden jar, and it is what is now known as capacitor and condenser or condenser. So next one, eighth is in 1746 circuits and currents were defined. This was done by the William Watson in 1748. So what he observed: discharge a Leaden jar through a circuit. This battery or that capacitor was discharged through the circuit of a conductive material. That conductive material, what he used? Wet thread, and introduced the concept of current. So here the concept of current was introduced through the discharging, and discharging was done through conductive material wet thread, which was just dipped in a salty water or like this something. Research continued into dielectric materials for greater charge storage in the capacitor. So capacitor was the innovation here, and dielectric materials were to be found for better capacitor. In 1751, Benjamin Franklin published theory of electric fluids, and the other experiment, kite experiment, was also done by him. So the battery, he was trying to discharge this condenser or capacitor. Condenser discharging was the objective, and for that he was studying about electric fluid, how to discharge this, or through which he could have discharged the Leaden jar. And kite experiment also well known. He tried to catch the lightning strike, and which can be stored in the Leaden jar. It was the idea behind kite experiment. In 1751 and 1754, what he observed: Benjamin Franklin, he published his book Experiments and Observations on Electricity in 3 volumes. The publication contained the first adequate explanation of how the Leaden jar worked. See, first his work was related to Leaden jar, and introduced his theory of electric fluids to explain currents in the circuit. So discharging was the motto, or discharging was his motto. So through his theory, though his theory was deficient in some respects, it was robust enough to allow other scientists to make great discoveries in the following century. Many of the terms Franklin introduced in his theory have remained in the use. Then further his studies was carried out by Ebenezer Kinnersley in 18th century. One of Franklin's collaborator, Ebenezer Kinnersley, 1711, his period is provided, dubbed two-phase two types of electricity as positive and negative charges. Kinnersley also pointed out that electric fluid theory did not account for the repulsion between the similarly charged bodies. So similarly charged means positive will have no repulsion, just positive and negative charges will have repulsion force. So further in 1785, electrostatic repulsion of the positive and negative charges were defined. So static repulsion and positive and negative charges were defined. In 1777, Charles Augustin de Coulomb. So Coulomb is introduced. It is a unit of charge. Coulomb is unit of charge. What he observed? He invented the torsion balance device capable of qualifying the attractive force of electric charges and magnets. Using this device, he published his findings in 1785, explaining the principle that governs the attraction and repulsion between the negative and positively charged electrical charges. So there is a force, and that Coulomb's laws were later confirmed. This force between the two charges is dependent on q1 into q2, their magnitudes, multiplication of these two charges and distance between these two. So principle that governs the attraction and repulsion between the negative and positively charged. So what is the principle? He just explained that through these forces. So different charges have different forces with respect to their separating distances. Then unit of this charge is Coulomb. Coulomb's law was famous there. Coulomb was named for his honor. So unit was given in after his name. Electric fluid theory could not be fully investigated as the only available charge sources and batteries, as Franklin coined them, were Leyden jar, and they discharged all stored energy in instantaneous burst. So this discharging was not controlled. It was just within fractions that completely discharged it. So what was needed was a longer lasting controlled current that could allow a more in-depth study. So this controlled discharging was not possible here, so that took time, and further innovations were going on. So this further, Luigi Galvani in 1737, what he did in 1791, Galvani stated as a conclusion of his study during the 1780s that frogs' legs, which had been preserved in salt water, were source of animal electricity, a new type of electrical fluid. But this was also not approved or not accepted by the Volta, and he declined his opinion that this animal electricity or that frog just is a reason behind the electric source. that frog was just twisted due to shock. In 18th century, voltaic pile allowed controlled discharge of the charged particles, superseding electrical fluid theory. So here, electrical fluid theory was absolute. So here, physicist Alessandro Volta in 1745 to 1827, by late 1800, he developed first practical battery. So battery was firstly developed in 18th century, 1800. Here it was possible for him that controlled discharge, but discharging resistance may be used. So here we can see first is metallic pile, in between is dielectric, is metal, dielectric, again metal, and the stacking was formed, and this was the battery, and this is the discharging plates. We can see this is the battery. Voltaic pile was the name. So through his friendship with Galvani, was aware of animal electricity theory prior to its publication, and started replicating the dissimilar metals experiments with the threads weighted salt water instead of frog legs. So different dissimilar metals were used to discharge the Leyden jar, and instead of frog legs, in the late 1780s, Volta tried to dissuade Galvani from publishing his theory, stating that it was a diseased frog, nerves reacting to the current that caused the twitching. His advice having been ignored, Volta set himself to categorically disapproving Galvani. So further, what Volta did? Volta proved that his theory correct with experiment. A current was carried through the wet thread between 2 cups of salt water. This with the different types of metals in each. By late 18th century, he had developed the first practical battery consisting of vertical stacks of couples of copper and zinc discs. So this we saw the battery. First is the metal stack, second is dielectric stack, so this was the like that this battery was done, and then this for discharging these metallic plates were used. So this was the battery like this stacking, and these discs were separated by the disc of cloth moistened in the salt water. The design is known as the voltaic pile. Publicly demonstrated in 1801, the voltaic pile did not build up as much charge as some Leyden jars. So this voltaic pile has not stored as much charge as Leyden jar. Leyden jar was found superior, but it could release the charge in the controlled manner. controlled continuous current instead of single burst. This was the advantage over the Leyden jar. The controllable current was the catalyst for electromagnets and great advances in the electromagnetic theory during the 19th century. So here controlled discharge led benefit that this controlled current was catalyst for the electromagnets and great advances in the electromagnetic theory during the 19th century. The electric potential unit, the volt, is named after volta, as is the instrument for the measuring electric potential, the voltmeter. So volta was named, volt was named after the volta, and this voltmeter is also named after volta for his honor. So his performance or his work is appreciable. In 1819, link between the currents and magnetic fields were observed. In 1819, Hans Christian Oersted, what he observed, link between the currents and magnetic fields. Now current and magnetic field density, this flux density, we can see there is a correlation between these two. He discovered between the electric currents and magnetic fields. Magnetic fields inductance is there, L is equal to N d phi by dt. So this was the relation which showed that electric currents and magnetic fields are correlated. And related to the flux linkage. In 1820s, currents and magnetic fields used to create the motion. So in Faraday's law of electromagnetic induction, Faraday's law of electromagnetic induction, induction was responsible for the motor motion. The first systematic experimentation and study of electromagnetism shortly after Oersted published his findings by 1820, Faraday had demonstrated how currents and magnetic fields would be used for the creation of the motion. So here EMF is induced in the conductor. Suppose this is a conductor and this is a magnet having N and S pole. So any one should be in motion and one should be stationary. So we say stationary magnet and conductor is in motion. So when we bring this conductor near to the magnet and keep motion, move forward and backward, so here EMF is induced in the conductor and then current starts flowing in the conductor. So this is the electromagnetic induction phenomena, and that is responsible for the motors, generators, transformers, all the electrical equipments which are having the fundamental of Faraday's law of electromagnetic induction. Then we have to build the stronger electromagnets and powerful equipments, bigger equipments. Then these need for the electromagnets of the bigger size was the need. So electromagnets were developed, allowing stronger magnetic fields to be used. This was done by the William Surgeon in 1825. How he did it and how he achieved that? he showed that winding means coil. Their coil is one which could concentrate the electric magnetic field. So how he did this? Showed that the winding, a current carrying wire around a iron bar concentrated the magnetic field. Electromagnets allowed the induction of the magnetic field that were much stronger than those occurring naturally in the lodestones. So this is a former, and coil is wound on it. So this coil with the number of turns n and the magnetic field generated was very strong when the current was flown or the AC supply was applied to the coil. Further, Joseph Henry in 18th century, in further innovations he carried out. He continued to experiment the electromagnets and discussed the self-induction of the circuits around 1830. Self-inductance explains the operation of the inductor circuit element. Unit of the inductance was termed after his name. Henry was named after him. Henry also observed mutual inductance, one of the circuit inducing the magnetic field in the another during the 1830s, but did not publish his findings apply to the practical use. So what is self-inductance? Suppose this is a conductor and current is flowing through this conductor or a coil. Say coil is there, and current is flowing. So here this current will cause a magnetic field around this conductor, and this flux will cut the conductor. Flux cuts the conductor, and which will induce the EMF, and that EMF is self-induced EMF. Current is flowing, that generates the flux field around the conductor, and that field cuts the conductor and generates the induced EMF. That is called self-induced EMF. So also we can say this self-induced EMF as a back EMF. Again, in 1826, Ampere law defines relationship between the magnetic flux and the current. So Ampere found the relationship between the magnetic flux and current. Flux is phi and current is I. So current is, so how these two are related? So it is in machines, electrical machines, current and flux are directly proportional. He formulated mathematical relation between magnetic flux and currents known as Ampere law. It was published in 1826 book Theory de Phenomena Electrodynamics, Theory of Electrodynamic Phenomena. Ampere showed that parallel conductors will either attract or repel. So these two parallel conductors are there. This will have proximity effect. We say proximity effect, and which have the attraction or repulsion forces between the two as per the distance, depending on the direction of the current flow, and invented the static needle and the galvanometer, the device that measures the current. the unit of current, the ampere, is named after him, as the galvanometer recognizes Galvani contribution to the understanding of the currents. In 1827, next further, Ohm's law introduces concept of impedance and admittance. Here Ohm's law is V is equal to I into R, keeping the environmental conditions constant. Means temperature change will change resistance, and resistance is directly proportional to rho L upon A. This is also resistance is dependent on the different factors, so resistivity and temperature and other things. This is the very fundamental formula used in electrical engineering, Ohm's law. Then in 1830, Henry explains self-inductance. Again, we have just discussed this. We were repeatedly coming across this inductance, self-inductance, back EMF. Self-induced EMF means we can say back EMF also. Joseph Henry is the innovator. Continued to the experiments with the electromagnets, discovered self-induction in the circuit around the 1830. Self-inductance explains the operation of the inductor circuit element.